Okay, so we will be talking about accelerators. Accelerators are very important in the field of particle physics. Okay, in particle physics, we are as overall in particle physics, our main task is to study particles, as the name says it. So when we study particles, we are studying, and to do that, we uh, we require or we accelerate them, accelerate them to high speeds. Okay, high speeds. Now the reason, and when they're on high speeds, they then we make them collide with each other. Okay. Now, for the collision, we have two types of collision, in which first or in which one is in which we will have a particle shot from a or released from a source, okay, and it will go and hit a stationary target, a stationary target. But uh, there are advantages and disadvantages, both advantages and disadvantages. Then the second one we know is moving targets or moving collision. The one with moving collision is where both particles, okay, are shot from the source and they collide at one point with each other. They collide at one point with each other. Okay, collide. Now the difference is that in first one we have a stationary target, it, to which a particle collides, but in this one we have both particles. We have two particles this time, which are moving. Now that advantage and this again same here. We can say the advantage and disadvantage of both are vice versa. The advantage here is a disadvantage over here, and the advantage for the stationary one is disadvantage for the stationary one is advantage for the non-stationary, where both particles collide with a certain momentum. Now, when we talk about um, when to use each type of collision, let's say we have collision 1 and collision 2. Now, collision 1, in collision 1, we can see that in this one, this target here has zero momentum before collision, and this has some momentum, let's suppose of any value, gamma. And in this one, in collision 2, we know that it has some momentum and it has some momentum. Now, since they're moving opposite to each other, we know that their final momentum will be this momentum minus this momentum. So what will be the final momentum? It should be zero, right? Because we know that the law of conservation of momentum is momentum before equals momentum after. So it should be zero. Now, using this law that momentum is zero after the collision, I should talk about C1 first, because C1 is mostly used for particles, So in C2, the advantage is that momentum after the collision is 0. What is it? 0. So now what's the advantage of the collision after collision, the momentum being 0? What's the advantage? It means that we have no kinetic energy. No kinetic energy. It's 0. Now this value, this kinetic energy being 0 is very important. Why? Because when we talk about energy of a particle, we have two types of energy summed together to give us total energy. Total energy, okay? Sorry. Total energy. Now, and it's sum of rest energy plus motion or the kinetic energy, okay? This is what the energy is. This is what total energy is all about. Now, since we have the total energy here, this 0. Total energy is 0 of motion. There's no kinetic energy, okay? The advantage we have for this is that all that energy, since it's 0, is focused on rest energy, means mc square, meaning the particle created after the collision, the particle created will be of larger mass. Larger mass. Advantage. That's an advantage. Second, all the energy, or the full amount is used in the formation of the particles. Formation of the particles. Okay, that's second advantage. Okay, that's second advantage. And even these are also advantages. Momentum being 0, that's also one advantage. Kinetic energy being 0, because when the reason these advantages, because if they are 0, that we don't have any kinetic energy and any momentum, is the reason that all that energy is used to create new particles. Now, since again the opposite for this one, if in collision 2 where we have two particles moving towards each other and they collide, if they collide, we have large mass. Vice versa. In this one, that means if a particle is colliding with a stationary target, the after the collision there's some momentum. If there's some momentum, it means it has some kinetic energy, or it has kinetic energy, not some, it has kinetic energy. So that means after collision, let's suppose if we have two particles, if we have a photon, let's suppose not photon, proton, and it hits a target, okay, and in the target's a particle, okay. Now that particle after the collision, after collision there are two particles made. Let's suppose pi minus and pi plus. I know it's not a reasonable collision because it doesn't conserve the loss. So it's just an example. In this one, these particles are moving with certain kinetic energy. Now, since they're moving with kinetic energy, the total mass is rest mass plus motion mass, motion energy, not mass, in energy. That means this is some value. Now, since motion has some value, this value over here must be less now, since then when we compare it to two particles colliding with each other, this mass, so we can say energy at rest for moving collision, we talk about moving collision means two particles colliding with each other, is greater than energy rest for hitting a stationary target. Okay, that's how it will be. So that's about the collisions of the two types of collision. And then when we talk about the two types of, now that we have talked about collisions, why not talk about the accelerators as well. I should start with accelerator first, but no problem. There are two types of accelerators. Okay. One is Linac, it's a name, also known as linear accelerator, and then we have a circular accelerator known as cyclotron. Interesting name, right? Cyclotron. Sorry for my if I wrote it wrong, the spelling. But now here in both, the difference is only that the only difference is that in Linac we only have electric field, but in cyclotron we have both magnetic and electric field. Okay, B and E. Now talking about the system, how they work, let's come to Linac first. Okay, when we talk about Linac, it's a straight line. Okay, it's a straight line. Okay, now in this straight line we have a particle which is shot from the source, or which is released from the source, however you want to say it, and it travels in the tubes. Okay, and it travels in the tubes. Now while it's traveling in this tube, okay, while it's traveling in the tube, it's being acted upon by the electric field. Okay, now when it's being acted upon by the electric field, let's suppose this is a negative particle, so it will be attracted towards the top and the bottom, right? When it will be acted by the top and the bottom, we can draw their components. Okay, we can draw their components, and the components will be one which is horizontal, which is sine theta, and same for the down one, sine theta, and for the horizontal we have cos theta. Okay, now when we look at their arrows, the resultant, for the resultant to be produced, this is for the down one and this is for the top one. We can see that the vertical sine theta for the upper one and vertical sine theta for the bottom one, they cancel each other, and we are remained with cos theta. Okay, so it's doubled. So what happens? It accelerates. Then in the middle there's PD. Okay, there's PD. Now that PD, what the PD causes, it gives energy to the particle. Energy. Okay, we know that as from the formula EV is equals to E. So when it is acted upon by the potential PD, it gains energy. It gains it. So, and the PD, the frequency of PD, or the potential difference is, the frequency is constant. Okay, it is constant. Now since it's constant, we require the length of the tubes. Okay, the length of the tubes to be exactly same. We want it to be same. Now when it will be same, right? So it means the amount of time spent in each tube is same because of frequency constant of the supply at the back. Now then, but the length, no, not same, sorry, that's a mistake I did. The length will keep on increasing. Let's suppose if this is first length, the second length will be length plus some increased length. Sorry, not length same, length increased. But in the end, the length will be same. Now, why will the length of the tubes at the end section, let's we convert into sections. This is section 1 and this is section 2. In the end section, we have all the tube lengths are same. Now, why is it same? It's same because it's same because as it approaches the speed of light, it approaches, not equal speed of light. It cannot happen, that cannot happen. So we have to be careful. As it approaches the speed of light, this causes, was it 1 or 2? This causes the velocity, the particle to start decelerating. What do you call it? Deceleration. Okay. That means the equation EV is equals to 1 by 2 mv square stops. This now doesn't apply. Okay. This, and what happens is EV is equals to mc square. Now, instead of velocity increase, the increase we see is of mass. Now the mass starts increasing as a consequence of velocity not increasing. The mass starts increasing. So it's useless. We don't. So then, that's why at the end section it becomes same. So we say that as V is constant, that means ST should be also constant in as well, because ST is V. Now then I think I covered everything about Linac. Am I missing something? No, yeah. So there's one thing I think I did talk about acceleration, that yeah, it accelerates the particle. I talked about it. Now then what was it? Yeah. Then we have cyclotron. In the cyclotron, the fun fact about cyclotron is it uses both the magnetic field and electric field. So to talk about cyclotron, it has a center, okay, in which there's a source, and source causes it to, and yeah, I should have talked about the structure as well. Cyclotron consists of 2Ds, okay, 2Ds together are known as cyclotron. And when the source is released, it has an increase of radius. So for a cyclotron, to explain it, we use an equation known as R or equal 1 mv over bq. The origin of r equal mv over bq is because we know that when it's moving in a circular path, it is acted upon by centripetal force, which is, to calculate centripetal force, we have mv square over r. Now, and for as we're talking about a particle being accelerated, and it has a force being acted upon by it, which is F equal bqv. We know that this F is same as centripetal force, is the centripetal force. This, so we can say bqv over r equals mv square over r. Okay, sorry, not where r coming from? Yeah. So then when we substitute it for r, we know that v cancels, so we have bq is equal to mv over r. Now r is equals to mv over bq. This is our new equation. This is the equation we use for cyclotron mostly. Now when it's increasing in radius, so we say that in between the d's is where the cyclotron or the particle will gain energy, and the PD over here, or the magnetic field over here and magnetic field over here, when it's over here, it will be a magnetic field which accelerates this particle, okay? But the moment it's in the in the gap, this over here changes, so that the particle is always accelerating in the direction of the field. Okay, the moment it's in the gap, the PD of the next, or the magnetic field of the next D changes, so that it's always traveling in the direction of the field. It's always accelerating in the direction of the field. And this is the only thing about the magnetic field. And for the electric field, it's the same as when we talk about Linac, with some differences. Here we don't have tubes. We have a single D, which is accelerating the particles in a circular motion. So that means we can say if there's an increase of radius, this causes the V to also increase. Velocity is increasing, radius is increasing. Because of increase in radius, there's an increase in velocity. Now here, the one important thing is that when we talk about R and V, this V over here is not the magnitude. Okay. The V in the magnetic field, okay, V in the magnetic field is not speed. Okay, it's not speed, it is velocity in the magnetic field, because as magnetic field is a deflecting field, it causes no change to the magnitude, only the direction changes. That's why we talk about velocity, not speed, for the equation. And yeah, that's it for the particle physics accelerators. Nothing much then. And there's one interesting thing I would like to talk about the Linac, is that, let's suppose when we talk about the Linac, okay, and it passes through all these 4 tubes, if we want to know at this point, after passing through the tubes, what's its velocity, So when we use ev equals 1 by 2 mv square, okay, be sure that when we talk about ev, electron volt times potential difference, we're talking about this ev in after passing through this single gap, or the tube. After this over here is, let's put ev, but after passing through this one we have ev times 2. Then again it's like third tube, ev times 3. The fourth, ev times 4. So it's increasing by the number of tubes you're increasing. So let's suppose if we have ev times 5, that's 5 tubes, 5 times 5, 6 tubes times 6, because after each tube you're being interactive with that potential difference again. You're gaining that potential difference, which causes the increase in kinetic energy, or the energy overall. Okay, and so that's why it becomes ev, n ev is equals to 1 by 2 mv square. This is the equation we use, this n being number of tubes. Okay, and yeah, that's it. And